Hello everyone. Let's start with something interesting. Have you ever noticed how, when you look into a swimming pool from under the water, sometimes you can see the world above you, and other times it almost looks like a giant mirror? That fascinating effect is all about today's topic, the critical angle. Light, as we know, bends when it passes from a denser medium like glass or water into a rarer medium like air. This bending is what we call refraction. Now here's the curious part. As you gradually increase the angle of incidence inside the denser medium, the refracted ray keeps bending closer and closer to the boundary surface. And then, something special happens. At one particular angle, the refracted ray doesn't escape upwards, but instead it travels exactly along the surface, making an angle of 90 degrees with the normal. This very angle of incidence is what we call the critical angle. So how do we define this more formally? The critical angle is the angle of incidence in the denser medium for which the angle of refraction in the rarer medium is exactly 90 degrees. In other words, when the angle of incidence equals C, the angle of refraction becomes 90 degrees. And remember, if the incidence angle becomes larger than C, refraction simply stops. The light can't come out, and instead it reflects entirely inside. That's the starting point of something even more exciting, total internal reflection. So you can think of the critical angle as a threshold between refraction and reflection. Let's work out the formula for the critical angle step by step. We'll begin with Snell's law, which states n1 sin I equals n2 sin r. Here, n1 is the refractive index of the denser medium, n2 is the refractive index of the rarer medium, I is the angle of incidence, and r is the angle of refraction. Now, at the critical angle, I equals C and R equals 90 degrees. Substituting these values, we get n1 sin C equals n2 sin 90. Since sine of 90 degrees is equal to 1, the equation reduces to n1 sin C equals n2. Rearranging gives sin C equals n2 divided by n1. Therefore, the critical angle is C equals sine inverse of open bracket n2 by n1 close bracket. This is our working formula. Now let's talk about what affects the critical angle. The most important factor is the refractive indices of the two media. If the denser medium has a very high refractive index compared to air, then the sin C becomes smaller, which means the critical angle itself becomes smaller. Take glass, for example. Its refractive index is about 1.5. So, its critical angle in air is roughly 42 degrees. But diamond is much denser optically, with a refractive index of about 2.42. That makes its critical angle only about 24 degrees. And that's actually why diamonds sparkle so brilliantly. Light inside them keeps bouncing around with total internal reflection before escaping, giving that dazzling effect. Understanding the critical angle isn't just about optics on paper, it's deeply practical. One of the most important applications is in optical fibers. Here, tiny glass or plastic threads guide light signals over kilometers using repeated total internal reflections. This is the backbone of modern communication, the reason you can stream videos, make video calls, and use the internet at high speed. Another application is in prisms used in binoculars and periscopes. They rely on total internal reflection, achieved thanks to the critical angle, to turn light by 90 or even 180 degrees with almost no energy loss. Diamonds, as I mentioned earlier, owe their sparkle to a very small critical angle. And even mirages in deserts, those illusions of water on hot roads, are a natural outcome of varying refractive indices where light bends close to the ground surface. Let's solve a simple problem together. Suppose the refractive index of glass is 1.5 and that of air is 1. What is the critical angle? We start with the formula sin C equals n2 divided by n1. Substituting values, sin C equals 1.0 divided by 1.5. That gives 0.66 recurring. Now, C equals sine inverse of 0.66. Using a calculator, we find C is approximately 41.8 degrees. So, the critical angle for a glass air boundary is about 42 degrees. Alright, let's quickly recap what we've learned today. The critical angle is the special incident angle in the denser medium where the refracted ray just grazes along the boundary at 90 degrees in the rarer medium. Using Snell's law, we derived its formula sin C equals n2 by n1. We saw that the smaller the critical angle, the more total internal reflection occurs. That's why diamonds shine, why optical fibers transmit data, and why prisms are so efficient in reflecting light. So to sum it up, the critical angle is more than just a number, it's the gateway to understanding total internal reflection and its countless applications in technology and nature. I hope this session gave you a clear understanding of the critical angle. I'll see you in the next session with another fascinating concept of physics.